Okay, good morning. Good morning, everyone. Thanks for joining. Today we are going to wait 1 more minute because some of our friends are still joining, so we will be starting soon. So thanks for joining this new webinar by VICUSdt. So we will be starting pretty soon. Please hold on 1 minute. Okay, so let's move on. So again, thank you all of you for joining for this new webinar. We have changed slightly the format compared to the previous webinars. This one will be a bit longer, but I think it will be also a nice format where we call it the VICUSdt Talks, and more of them will come. But this is the first one that we are focusing on silent propellers. So for this new format, we will be talking to some, I will call them industry leaders in their fields. So we have invited 3 main actors in the silent propulsion world. So our agenda for today will be that we do first a 15-minute technical introduction that I will be doing myself, focused on the several topics related to the quiet propulsion design. And then we move on to the 30-minute roundtable that we call the Quiet Propulsion in Practice Industry Perspectives, where we will have 3 of the main players in the shipbuilding industry doing their explanations and their experiences in the field of the Navy submarines, research vessels, and unmanned vehicles. So let's go for the presentation. So we welcome Bienvenido Alonso. He's the head of submarine hydrodynamics at Navantia. Navantia, as many of you know, is one of the leading Navy shipyards in Europe, and Bienvenido is a naval architect. He has been working on the submarine hydrodynamics for 2 decades, and we are very happy that he can share some of the insights of the hydrodynamics for quiet design of submarines today. Then Santiago Martín is the managing director of the biggest shipyard of Armón Group, which is the biggest shipbuilding group in Spain. And Santiago has accumulates several decades experience working with silent propeller projects in their oceanographic research vessels, which are among the quietest in the world. So he will bring the perspective from the shipbuilder on how to bring the scientific concepts of quiet propulsion to the slipway.
Good morning, everybody.
Welcome, Santiago. So, and then Stéphane Vannuffelen, it's from EXAIL, which is one of the leading companies in the unmanned vehicle design and construction for different roles. And Stéphane holds an engineering degree in physics from and has been working also for more than 20 years experience in the fields of offshore and research for underwater noise, and he will explain also about his experience with the EXAIL unmanned vehicles and some practical cases. Okay, that's me. Some of you already know me. I'm the managing director of VICUSdt, and we are a ship propulsion consultancy specialized on ship propulsion and engineering. Okay, so with the first part, as I said, I will be doing a brief introduction on certain interesting topics, which are not purely propeller hydrodynamics, but more the connection with the practical aspects related to the shipbuilding. So we will be 5 blocks in these 15 minutes that are the rules and regulations, what are the service and the mission of the vessel and the constraints, what is the impact of the hull design, how it influences the propeller, the main particulars of the propulsor and also just a bit of insight into the propeller details. We were joking yesterday that we might spend 1 hour talking only about only one of these slides, because you can spend the whole day talking about the standards, you can spend 2 weeks talking about the service conditions or hull optimization. But the idea of this block is just to give a very brief overview on several topics that will help us to move on during the roundtable. Okay, so regarding the rules and regulation, just some brief notes are regarding the first. We talk about the people is a bit scared about the upcoming IMO MEPC that was recently approved. There are some guidelines for underwater radiated noise. So there is now an experience building phase going from 2024 to 2026. And maybe there are some mandatory limits coming after that. So we will see where this takes us. But this is a kind of a warning for the market that things are moving also at the IMO level. So it's not only Navy and research vessels, but also what can be mandatory for other type of ships. The EXAIL and the CII is all in place, it's all under control, but it's also linked. According to IMO, there might be a link also between that, because the more efficient vessels should be more quiet because they use less energy to propel through the water. But on the other hand, when we stress the propeller design for efficiency, we are also going in the opposite direction compared to the silent design, as we will see a bit later. Then the ICS 209, some of you will be familiar with it, and also the class rules, the class notations for silent vessels. We talk about the underwater noise curves, like we can see here, this, thanks to Armón, we have these 2 pictures of these nice ships built in Vigo, Armón shipyard, and also the image that you see, the curve you see there is the ICS 209 limit, which is the red curves, and below you can see the noise signature of those vessels. That is the blue curves, which have been recorded with the sono buoys. So we can see the compliance, which is very important for this type of vessels, so they can accomplish this mission. So you have 2 ways of complying with the curves, either the ICS 209 or a class rules, like the silent notation by DNV or Dolphin, by RINA or others. Then when we talk about the underwater noise, we mostly are talking about cavitation control. So sheet cavitation, but mostly it's tip vortex, what we have to control. We have to delay the tip vortex inception. And this is what we have to keep in mind when we are talking about compliance, one of these underwater rules. So very focused on, for the designer to control the tip vortex inception. And then regarding the comfort standards are somehow connected to the quiet propellers, because the pressure pulses transmitted by the propeller are also an important driver for the vibrations and noise on board. And so there is also a connection there. When a ship has to comply with the comfort standard, in the end, you have to make a silent propeller. And last but not least is the ice class. The ice class is affecting the thickness of the blades, and this might have an impact on trailing edge flow separation and leading to sinking propellers. So we will talk a bit about that later. Okay, next one is the service conditions. We are paid, the shipyard is paid to design a vessel and build it to comply with some requirements, but the owner is sometimes requesting things which are very challenging, no? So they want efficiency, but they want hydroacoustic performance, and this takes us to a difficult compromise. So making a quiet propeller compared to a very efficient propeller is not always possible. So we have to make it quiet, complying with any of the standards we mentioned earlier. Implies very often losing easily 5 to 10% efficiency, depending very much on the project. But in a challenging project, the efficiency loss can be significant, and this must be kept in mind. When we talk about the silent speed that we state in the contract, it's important how far is from the top speed, because we cannot make a small hull with a silent speed 11 knots when the top speed is 12 knots. And this is because of the Froude number that you all know. This will lead to a very loaded, highly loaded propeller thrust coefficient. And this also difficults a lot the design of the propeller. So typically, small ships has a compliant silent speed on the low range, say 8, 9 knots, while bigger ships are more in the range of 10, 11 knots for the noise measurements. And when it comes to the maximum speed, it impacts on the design of the propeller as well, because when my contract states that I have to comply a top speed, which is very much on the edge of the hull design, I need to squeeze my propeller to be efficient also to reach the top speed in the contract conditions. And as you can see in this graph on the side, sorry, the slide was wrong. This is an example, a ship designed for 12.5 knots and a ship designed for 14 knots. So probably the ship will not be sailing much faster than 12.5 or a bit more. But the difference in the efficiency of the propeller, you can see here, we have 45 kilowatts. So it's a 5% efficiency because one propeller was designed for 14 knots, while the other was designed for an engine only to reach 12.5. So if the ship really doesn't need this extra knot, it will have a cost to keep it for the rest of the life of the ship. So it's very important. This is more a talk to the owners, not to ask for too very high speeds, because you pay for that in the efficiency and also in the silent design of the propeller. Okay, and then for the tow pool, especially for the fishery research vessels, there is also a requirement in the tow pool by towing a net or typical research net. And this also has an impact on the tip load, especially if it's a ducted propeller. So take care also with that. Okay, going into the hull, then Santiago will talk a bit more about this. So I will go about this quick. Is the obvious the resistance is not a secondary factor, but is critical, because if I lower the resistance, I reduce the thrust needed by the propeller and makes the life of the propeller designer much more easier. Thrust deduction and wake. And when it comes to the wake field, it's obvious that going from single to twin screw also makes the life much more easier for the propeller designer, and we can make a more efficient and quiet propeller. But obviously the twin screw configuration is not the cheapest. But if the project allows, or a challenging project, when you go twin screw, is much more easier to comply with all the requirements.
Adrián, excuse me, I believe you are having problems with the slides.
Yeah, sorry.
Okay.
Here it is. Yeah, the single and the twin screw I was showing. So you can see here the single screw wake field and the twin screw wake field, where you can see here the shadows of the shaft brackets and the shadow of the shaft still is having an impact, but is way less than when you see the single screw. So this is the impact the wake has in your project. And the same happens with the rotation of the shaft. When you go with on a twin screw, ideally you should go for a rotation inwards. That's the way. So the propellers are rotating inside, so you unload the propeller. That's an easy decision and also has an impact on the load of the propeller and the cavitation performance. Okay, here then this is just a comment on the model and full scale analysis. When you do the test on the towing tank, you go for a model scale analysis of the wake field, and the tests are done in model scale, but in the CFD you can run the full scale. So here we can see the comparison. Those two pictures below is the comparison between the model and the full scale. You can see in the model scale, due to the thickness of the boundary layer, the wake field looks bigger, but in the reality, in the real ship, we are here on the left. So keep this in mind, because on the tank predictions, things could be a bit pessimistic, and the real life, the results in the full scale tests are demonstrating that are better. Okay, just the two last ones. on the main particulars of the propeller. So now we talk about real propellers. The first decision, once you have your hull, you optimize your wake field, you optimize your appendages, the gondolas and everything. You convince the owner not to ask for a lot of thrust, a lot of speed. It's time to go for the propeller. And most of the configurations are open propellers for quiet ships, research vessels mainly. But there are some cases on ducted propellers that this one we have on the picture of the right, which is a nice class ducted propeller, also compliant with the underwater noise requirements. When you do put a nozzle, make sure you make a custom nozzle. So not the standard 37 or 19A. The standard nowadays is to make a custom nozzles, typically shorter nozzles with custom profiles. The construction cost is almost the same. And the interaction with the propeller tip is much better. So this is a good step to consider. For the fixed or controllable pitch, fixed pitch is the standard. And if you go for controllable pitch, which gives you also a lot of flexibility, despite it's much more expensive and not so optimal, take care with the hub vortex, because you might end up having a very strong hub vortex. And I think later on Bienvenido will mention about that, because that's also another problem with the submarine vessels. When you unload the tip, the load goes to the hub. So in the CP propellers, that is more critical. And regarding the RPM, the tip speed is the parameter to control, which is typically should be between 17 and 22 meters per second at silent speed. And top speed, you can find yourself in 25 to 28 meters per second. So you can keep these figures in mind when you are making some numbers for your project. And going over the tip clearance, the tip clearance is something that people typically keeps 20-25% of the diameter, but you can really go to less figures, so 15 even. So shouldn't be a problem as far as you control the tip load. So the tip clearance is not a fixed value, depends a lot on the load on your propeller. So maybe it's better to have a larger propeller with an unloaded tip, and even if you are closer to the hull. So keep that in mind as well. And regarding the blades, 5 to 7 blades is the standard. No need to put more blades. Okay, and then final slide, and then we go to the chat. Regarding the sections and camber, we can see here on the top of the slide this profile, the original section in red, and how it was modified on a silent propeller. Then the modified section, you can see how is the change in the sections and in the camber. Below, we can see how is the camber modified, original camber, more camber on the leading edge, and then we go to less camber in that area. So when you talk about the circulation, that is, for those of you that don't know, the circulation is how we distribute the load radially on the propeller. This is the circulation distribution for a silent propeller. We want to shift the load from the tip here on the right of this curve to the center. So we have this belly here, but not put too much load on the root, because then I will make a very strong hub vortex. So it's a trade-off. Try to go to 0 on the tip, increase the load in the middle, but not too much. So you have, in this area, you need to find a balance, a trade-off between the load you put there, but not to overload too much the profiles. And final comment is regarding the trailing edge. You remember I mentioned the ice class propeller. So for the ice class propeller, you have to make thicker edges in the leading and the trailing edge. So those thicker edges can be a problem, despite it's good in the leading edge, in the trailing edge can be a problem because of the flow separation there, which can generate singing. So the anti-singing edges on ice class propellers are very critical, and you have to study that part very carefully, because having a thick trailing edge can generate flow separation very easily, especially with unloaded tips. So it's very dangerous, that area, the tip with an ice class propeller. So pay attention to that when you design your propeller, because the anti-sinking edge, there are different options that many of you are familiar with, like suction side only, rounded one, both sides, and combinations of them. So it's a lot of science behind this thing, and it's very tricky to tune. Okay, so I think that's all from my side. I already exceeded a bit the time, and I think now it's time to go to the. We have a few slides that were prepared by our friends joining us on the round table. So now I will give the floor to Bienvenido, because I have some questions. Bienvenido, hello, welcome.
Hello, everybody. Okay. Then,
okay.
Well, I will show
Bienvenido.
you.
I just want to
first.
Yeah, I want to ask you about about the technologies and the status of the state of the art in the submarine propulsion design, and what are technologies that you think are most promising today to optimize the cavitation in modern submarines?
Okay. Then, as you can imagine, the design of propellers in submarines are a very complicated thing, because the main is we have highly demanding requirements. Acoustic signature requirements, and the usual question in propellers in submarines, it's that we sacrifice the performance. Then, sacrificing the performance, trying to attend in the requirements about acoustic signature. Usually in propeller of submarines, it's that the cavitating noise is not very important, because the thing that we have to do to avoid cavitation is go deeper. Obviously, then the non-cavitating noise becomes relevant in this kind of propellers. But when we go to a snorkel depth at periscopic depth, we are at depths usually found in the surface ships. Then we have to install cavitation. We have to design the propeller attending to the several cavitation control techniques. Main control techniques, and in my experience and experience of everybody in this business, it's you need to have a wake control very important, very strict. Uniformities in the wake are the main cause of cavitation. Then, after control the wake, if you have to mitigate the effects of cavitation, you can use the high skew, not too much, because especially highest skewed propellers has additional problems for the submarines. But you need to make a high skew propeller to try to mitigate the cavitation. And the two main techniques to control the cavitation, it's first of all is unloading tips. It's the main topic that you have to keep in mind when you need to avoid cavitation. Means you sacrifice the performance, you sacrifice the efficiency, unloading tips, but it's the first step to avoid cavitation here after wake control, you remember. Then when you unload tips, you get avoid the tip vortex cavitation, and the inception of cavitation should be done by hook vortex cavitation. Then you have to, you could be back a little bit, only 10 seconds. To control the hook vortex cavitation, that is the main problem now. If you have made the things correctly, you need to put something in the hook, like you can see in the photograph. It's not an ESD, an energy-saving devices. It's a special thing to try to distort the vortex produced by the roots of the propeller, or by the roots of the blades, and try to mitigate the joining, the tendency to join the vortex of the roots in the hook, sorry. And then this is the main way to try to mitigate the hook vortex. That is our main concern today. End of file.
Okay, that's a interesting device. That's we don't in the ships. We have the PVCFs, but are working with a different idea in mind. But
yeah, this device is not for saving energy.
Yeah.
This device increase the energy necessary to move the submarine, but a little bit, and reduces cavitation risk.
Okay, interesting one to see this. You don't see many submarine propeller pictures very often. It's typically very restricted to.
Yeah, no, this is an internet file from a German submarine, if someone is interested. It's not the Spanish submarine, don't worry.
Okay, thank you. I will also wanted to ask Stéphane about then we will come back to the submarines, but I want Stéphane to join us and comment a bit on the unmanned surface vehicles, because with I think EXAIL has an interesting product now on the market with several running around, and unfortunately the drones are in fashion now because of the extensive use in the world, but I believe there is a promising future now that a lot of companies are developing this type of solutions, and I believe EXAIL has a good one. So, Stéphane,
yeah,
what is from the point of view, the biggest challenges when to integrate a small propeller on a small vehicle with a high power density, but still you need efficiency and you need to be very silent because you have very, well, I would say big gondola, but also very expensive hardware below the propeller, as we can see in the picture, that is obviously being affected by the propeller.
Thanks so much, Adrián, for giving me the opportunity to provide our perspective regarding low noise propeller and the impact of the acoustic signature on USV operations. So I do work for EXAIL, we're a French company, and we are manufacturing the Drix USV family that you can see on the picture. So we have a Drix H8, 8 meters version, and the Drix 016. And in August, we started a collaboration with Adrián and his team, regarding optimizing the propeller design for Drix 016. So these USV are mostly designed for hydrographic applications, seabed mapping. And in 2024, we launched the Drix 016, that you can see a picture of it currently. This Drix 016 is equipped with a full ocean depth multi-beam echo sonder from Kongsberg, so-called EM304. And this multi-beam echo sonder is designed to do seabed mapping to water depth in the range of 5,000 to 6,000 meters. It's a fairly big antenna. It's installed in a gondola below the Drix Ocean. So the antenna is in the range of 2 meters wide and 4 meters long. And as Adrián mentioned, since it's multi-beam echo sonder, the signal-to-noise ratio is super important in terms of maximizing the operating envelope of the multi-beam. And any noise received by the receiving part of the echo sonder will degrade the performances. So we started the integration of the EM304 in July, and we realized that the free blade off-the-shelf propellers that we were using at that time was too noisy. It had a fairly high level of cavitation that was impacting the multi-beam performances and maximum, depth range. So following this, we contacted VICUSdt in beginning of August, and to start a study around a new design, knowing that we had a very strict deadline because the vessel was leaving Marseille to go to Lisbon in the beginning of September to participate to REPMUS. So it was a very, very tight deadline in terms of designing a new propeller and manufacturing it. And at the end, VICUSdt delivered, and it was very good experience from our standpoint. VICUSdt was really on time in delivering the propeller. It was fitted on the vessel 3 days before its departure. And out of the noise characterization that we did, we gained something like 15 dB broadband noise in between 30 and 40 kilohertz, where the EM304 operating, resulting in a significant range improvement for the multi-beam echo-sounder. And in REPMUS in August, we managed to do seabed mapping down to 5,000 meter water depth, and it was very successful. Our client was Oceanographic, which is the hydrographic hydrographic institute for the US Navy. And I think we got some good feedback from them in terms of the overall performances of the vehicle, and the propeller was one key component of it. So once again, thanks to the entire team in VICUSdt for their dedication, and they've really been a part of this success, European success, as part of the REPMUS operation. In some instance, the Drake's Ocean was operating in sea state 5. We had wave 8 in the range of 5 to 6 meters while still doing seabed mapping operation. So it was the first time, USV demonstrated deep water seabed mapping capability in such a harsh environment. Thanks so much.
Okay, very interesting. We believe for this type of units, there are a lot of constraints also in the size of the propeller, because if you make it bigger, also you are getting closer to the gondola. But still is a very interesting concept, but still the load on the propeller, that is the load in terms of kilowatts per square meter, was quite high compared to the normal standard. So indeed was a challenging project, but it's good to see we believe there will be a lot of opportunities for unmanned vehicles and that are designed for this type of roles or military roles. Okay, thanks, Stéphane. And I want to go to ask to Santiago about when it comes to the hull, how is the challenges because of the integration with the gondolas? Because in the experience we have had, the gondola can have, as I mentioned before, can have a huge impact on the resistance, but also affecting the wake field. And Santiago, how do you see, what are the developments that you carried out in the last 15 years?
Hello, everybody. Thank you very much, Adrián, for inviting me to talk about these extremely interesting things. Just for you to have a quick idea of our long road with VICUSdt, we have been building research vessels with VICUSdt during the last 15 years, more than 12 units, and most of them complying with ICES criteria and with very restricted URN, underwater radiated noise signature. So first of all, just for a brief explanation, in research vessel, there are the most important for the ship is the presentation card, let's say, is the possibility of the performance to do a bottom data acquisition or to do fish stock assessment. No? And for both, what they need is to be completely quiet. Let's say there are two killers for the multi-beam transducers. First of all is the noise, the own noise created by the ship, and second is the bubbles. So first of all, and then both are related together, and both are very related to the propeller design. So first of all was to try to study how we should define the forward body of the ship without bulbos, with a straight forward body, vertical. And most critical was the interface between the hull and the seawater. And in that interface, we have the bigger creation of bubbles, and how the bubbles has been studied through the 3 streamlines assessment. That's something we did with VICUSdt from the very beginning in 2010. We started to study how was the road or the path of these bubbles into the gondola, because if you remember, we started or the beginning of the design of gondolas was with the gondolas very far away from the hull. This was creating a magnificent performance in terms of acoustics, but it was creating a big hull resistance. It was increasing the fuel consumption. It was having a big impact in the depth of the ship. So we were having problems, for example, with low waters, working in low waters, and also it was affecting a lot to the steering of the ship. So in that moment, we decided to create something much more flush to the ship, and trying to reduce, let's say, or to increase, in fact, the noise coming from the propeller into the gondola. And that's why we created such kind of design, which was much more integrated on the ship bottom, and it was creating a path for the bubbles, the possible bubbles created in that interface, surrounding the area of the transducers. So, and this has been a big, let's say, improvement, not for the ship from the acoustic point of view, but also from the operation of the ship. This was step by step, we were changing and modifying the design in order to optimize all the different necessities we were having. So this is regarding the gondola. Then regarding the propeller, I don't know if, well, regarding the propeller, the most important, as you have been talking, is first of all, as Bienvenido said, unfortunately, in our case, we cannot go deeper. Surface ships, we would like to go deeper, but that's not a possibility. And most of the times we are, let's say, confined by the maximum draft of the ship because they are working in shallow water. So in that sense, and the second thing was that it was clear that for us, it was needed to have a big distance or a big clearance between the tip of the blade and the hull form. So with that constriction, the first thing was to try to improve the wake field. We have the experience, as Adrián has been explaining. It was a surprise for us, the big improvement we got when we were having two shaft lines instead of one, and that was mainly because of the nice wake field we were getting. So the other possibility to say was, okay, let's say the valve that we were taking out from the forward, we decided to implement it in the aft. And that was the way of having a nice and homogeneous flow of the water into the propeller. So once we got a nice wake field, the second was, of course, reduce the RPMs. The diesel electric mode of the ship was allowing us to work in very low RPMs, increase as much as possible the diameter of the blade, and then reduce the kilowatts per square meter in the propeller. And mainly, the big killer of this propeller was the tip vortex. And for the tip vortex, we have been doing big improvements, mainly with VICUSdt, but also with DMV, with the tip vortex index they are working with. And both together, we have created propellers, very low noise propellers, but also trying to increase the efficiency as much as possible. But as you have been saying, the ice class, for example, or the increasing or number of blades, as we had with Tom Crean we were building a ship with 7 blades, which was perfect from the sailing point of view, but it was, let's say, reducing the efficiency of the propeller. So it's always a big compromise. And then a good result we are having also is the bulbous rudder, which is reducing the let's say the pressure created in the aft of the propeller. So at the end of the day, I would say, and just for summarize, step by step, we have been doing new designs and new small developments, using a perfect tool, which is CFD, which is giving us big flexibility, and it's very fast response comparing to the towing tank. And it's perfect to compare and to optimize small things one by one. And in this road, we have been working together with VICUSdt, I believe, successfully.
Okay, Santiago, thank you. And I think we have a couple of minutes left. I have a question that is more or less open for all of you. That is but maybe Bienvenido, you can comment, because I'm also curious about how is the trade-off. Santiago already mentioned the trade-off between propeller performance and silence, but maybe on the Navy projects, the performance I'm talking about fuel performance, is not so critical, but and the pure interest is going into the noise. But I think for the endurance of the project or the ship, it also plays a role. Do you have any comment about that?
Yeah, that's the real difficult of this is the compromise solution, as Santiago said, because performance efficiency is sacrificed, but not always, because you have not a nuclear submarine. When you have a nuclear submarine, you sacrifice always efficiency because you have a lot of energy. But in SSK, in a AIP submarine or in a diesel electric submarine, the kilowatt it's very expensive, and you need all the kilowatts possible. Then the performance is not so easy to sacrifice it. You have to negotiate and you have to be careful with these kind of things. I completely agree. At the end, it's a compromise solution, as usual. Sorry.
Okay, and you, Stefan, do you have what is the trend with the endurance? Because I was surprised when you mentioned that the Drix sail from Marseille to Portugal. It was a non-stop trip, no? For how long or what is the range of the?
Yeah,
how is the compromise with the acoustic performance?
It was a non-stop trip, and the Drix Ocean is designed, for 30 days of endurance. So we're start talking about fairly long endurance, and the energy efficiency is super critical. It's the same as Alonso. For us, kilowatt is super expensive in terms of space, volume, and it's always a fight toward having be as efficient as possible. On the other end, we are thinking that it also depends on customer, in terms of the efficiency. For some of them, they will be more interested in having a silent propeller and lose a little bit in efficiency, and other one might be more interested in the endurance part. For example, if you are doing shallow water seabed mapping, the signal-to-noise ratio is less of an issue, for example. If you're doing fish stock assessment, the noise can really be something very significant, and you might be able to compromise on the endurance. So we don't think it's going to be one solution fit for every customer, but more kind of having different solutions in terms of propulsion depending on the application and the client.
Okay, and the last one is Santiago, about how do you see the trends for the future? Do you detect that the customers or the let's say authorities or what your customers are asking for? I'm talking about non-research vessel. I'm talking more about the normal customers, more concerned about the underwater noise from the propulsion or in general from the ship.
Of course, let's say the number ones in this is research vessels, but seems to be that there's a new trend about noise, mainly in harbor and in coastal areas. So most probably we will have some new rules in the near future. I believe that the big trend with research vessels will be the use of AUVs. So that will allow the ship most probably to work in lower speeds, which will be very beneficial from the low noise from the URN point of view, so from the noise radiated water point of view, and to be working in parallel many AUVs with the research vessel. Probably this is the big impact, but what I always say is that the first thing we ask when we start designing a ship is which is the profile. So the profile of the ship is very important. If we know that the power curve is very flat in this kind of ships up to 10, 11 knots, and everybody knows that they just need to develop this data acquisition at the speeds below 10 knots. So that means that the problem starts when they want to sail up to 15 knots, for example. This is or for example, in the fish research vessels, the big problem is when they want to have a big pool, and then you need to install special nozzles that we have been, let's say, designing with you together. So you need to start with the profile, and with the profile, probably you can, if you have different profiles, then you need to start to talk about hybrid solutions in terms not only the propulsion, so not only diesel electrics, PTOs, PTIs, but also the possibility of working with different propellers in different situations. So if you want to be molar pool, it's clear that azimuth thrusters with nozzles is the best option, but of course not for that acquisition. Probably we will find a way to have hybrid solutions to get a better performance in each different operation of the ship.
Okay. So I think well, it was quick. We ran out of time, and I don't know if Bienvenido or Stéphane, you can make, or even you, Santiago, you want to make any last comment, and then we leave some room for our audience to ask questions. I hope they have a lot of questions, and we will be happy to answer. But first, Santi, Stéphane, Bienvenido, do you have any final comment?
No, so final comment for me is, once again, it's a super important topic for us, and beyond, the pure civil application, we also see a lot of potential for more kind of military-driven application, where the noise is also a super important parameter. So I think our collaboration with VICUSdt, it's a beginning, and whether it's for DriXO 16 or the H8, we hope to have a kind of long-term technical partnership to optimize parameters that is absolutely essential to the overall performances of our vessels. So.
Okay, yeah,
From
you
my-
have now Armón there. Maybe you can sell to Santiago one of the drones.
Hopefully.
Yes.
For sure, it
Bienvenido.
would be a cheap solution. Yes.
We're making a special this week. If you buy 10, you get one for free. But
Perfect. Perfect. Good to know.
No, from my side, only to say thank you to everybody to hear my dissertation, and only remember to everybody that the secret is to adapt to the new things that come to your office in propellers, hydrodynamics, or whatever you do. It's to adapt the new things. It's the rest, study and survive. And thank you so much for everybody.
Okay, thank you. Bienvenido. Okay, so I think let's see if there are some questions from the audience, and feel free to ask anything about the presentation or related to the underwater noise from propulsion. Okay, we have the possibility for composite propellers we look at that, and are the advantages significant enough to look at further? Philip Jeffers. Okay, Philip, thank you. Yeah, with the I tell you our experience with the composite propellers, not really a carbon fiber, or when you mentioned composite, I talk about everything that is not, let's say, metal. We had had some experiences with composites, machined or 3D printed propeller, but with low power density. We found issues with the finishing is normally very good, and I think they are perfectly fitted for the purpose. But we found if you want to make it strong enough, it's not cheap solution. But for me, it looks promising, especially for a small application. I don't know if Stéphane, you have any comment about that, the possibility of composite propellers?
Well, we are, as a shipbuilder, we are specialized in composite build. I don't think we looked at, using a composite. I think for me, it's more about the long-term reliability, and it's an interesting question, but at least it's not on our short-term roadmap. For us, it's more broadcasted at this stage, and it's also a trade-off in terms of cost. I guess going composite, I'm not sure it will be so cost efficient, but
yeah, we found that when you do the structural the structural analysis mapping the CFD pressures on the composite propeller, you have to take care a lot with the stiffness in the radial direction, because we found that in some analysis we have done, the deformation of the blade can make that your careful design you do with the hydrodynamics must take into account this deformation that will affect the load on the tip and other parameters. So that's makes the design a bit more difficult, Philip. That's my experience. Okay, then Andre asked the CLT propellers used for asylum vessels. I will tell in the end, the CLT propeller is tip loaded. That's the acronym for the CLT. So the tip loading normally goes against to be silent, because it's very delicate to have the tip loaded can be CLT, which is more straight closing plate, but also the couple from used previously by MAN or others, not with you increase the load on the tip with the rake. And we found very challenging, because any small misalignment with the flow can make a flow separation there on the tip, where you are rotating 20 meters per second and can create a mess very easily, especially in this. It's better for the efficiency, but I think for low noise, I still would stick to more conventional approaches, despite you pay the efficiency loss. I don't know if any of the
our experience, Adrián, our experience is, as you say, every time we have unloaded the tip, usually the big problem in research vessels is in case the tip is loaded, then the inception of cavitation comes very early. So every time we have unloaded that tip, we have gotten very nice results with inception to cavitations over 13 knots, which is perfect, let's say. The big problems of unloaded tips is mainly the singing, which is not so under control nowadays, but it has a very easy solution. So, but in terms of cavitation, for sure, try to unload the tip. That's the way of doing it, at least in research process.
Okay, thank you. I don't know, Bienvenido, do you have any experience in, at Navantia with this type of propellers?
Completely agree. Unload the tips is the main way to reduce, and be careful with the trap of the singing. But against the singing, once you have solved the tip vortex cavitation, and then you fight against the sing. And singing is change trailing edge in tricky ways until you solve the problem. There's no magical solution for this, but at the end you fight and you win. Don't worry.
Okay, yeah. With regarding the tip unloading, we also had some cases where if the wake field is very, which is probably not the case in the submarines, but in single screw ships happens sometimes, that if or twin screw vessels, if the wake field differs a lot from the top of the propeller to the bottom, the local angle of attack can even become negative. So you have to take care with that, because you unload the tip so much that your tip is almost on zero pitch, and then you might end up having negative circulation, which is not bad at all, but it's also not to unload without control. It's always need to be done in a controlled manner, because then you might end up on the other side. And also this unloaded tip creates an unstable flow because of the change of the angle of attack, positive to negative, and can create also a mess there with the flow separation. So, okay, so thanks for the questions, Andre. Any other questions from our audience? Any curiosity, any technical issue, anecdotes? Okay, if you have any further concern, feel free to forward an email, and we will come back to you. Okay, I want to put the closing slide. That is this one with our contact details. So if you forward the email there, we will redirect to the speakers and come back to you. So thanks for joining, and I hope you enjoyed despite these final technical issues. Thank you. Thanks for the Santi, Stéphane, and Bienvenido. Thanks a lot for supporting on this.
Thanks so much.
Okay, bye-bye.
Thank you, everybody. Bye.
Bye-bye.